Hey guys, what's up? I hope this video finds everybody safe and healthy, and I hope you guys are finding ways to enjoy quarantine. Last week we learned a little bit about forces, and yesterday you learned some things about Newton's first law. Today we're going to kind of tie those two ideas together and take it to the next level. So, what we ultimately want to be able to do, this is learning goal 6.2, is create net force diagrams and use them to analyze the motion of different objects. So, like I said, taking that Newton's first law and tying it into the forces acting on an object and how that affects its motion. So, for this, you're going to want something to write with, pen or pencil, paper. You're going to need the list of forces from last week, which I will put up on the next slide in case you don't have that handy. And you'll also need, as always in science, your brain. So here's that list of the different types of forces that you learned about last week. If you didn't already jot those down, go ahead and make a list of that now. You're definitely going to want that handy as we go throughout these slides. Okay, so a little review. Newton's first law of motion, we call it the law of inertia. You'll hear it one of two ways. An object in motion stays in motion until acted upon by an unbalanced force, or an object at rest tends to stay at rest until acted upon by an unbalanced force. The other idea in there is the idea that an object with more mass has more inertia. So in other words, it wants to keep doing what it's doing more than an object with less mass. All right, so throughout this, what I want you to do is copy down the force diagrams as we draw them on the screen. So, number one, we have a marble that is just sitting on some sort of surface, so it's at rest. We want to think about what forces are acting on the marble, why the marble is at rest, in other words, why it's not moving, and what would cause the marble to move. So, forces acting on the marble. Go ahead and look through that list and see if you can come up with what forces you think are acting on the marble while it's at rest. When we draw our diagram, which I want you to copy down as we go through this, we're going to use a square to represent the object that we are looking at. So the square represents the marble. One force that is acting on the marble downward is gravity, because gravity acts on every object that's on Earth at all times, and it pulls us down towards the center of the Earth. So we're going to draw an arrow down, and we're going to label that with gravity. The next arrow is going to be up. It's counteracting gravity, and that is called the normal force. So the normal force is, remember, the force that acts on objects that are resting on a surface. So since the marble's resting on a tabletop or the ground or something, it has the normal force that's counteracting gravity. Those are the only two forces that are acting on a marble that's at rest on a surface. So we have gravity down, normal force up. Notice that I drew or made the arrows the same length, and that was purposefully because these forces are balanced. And that answers question number two. Why is the marble at rest? Why is it not moving? Because the forces that are acting on it are all completely balanced. So it is at rest. And what would cause the marble to move? Well, an object at rest tends to stay at rest until acted upon by an unbalanced force. So it would take some sort of unbalanced force to cause this marble to move, whether that's an applied force that goes to the left or the right, or maybe that we remove the surface and then there's no more normal force, so it falls due to gravity. Whatever it is, we need an unbalanced force to move that marble. All right, next example. We have some skydivers. Okay, so number one, what forces are acting on the skydivers? Let's draw a diagram to represent this. So here's the square that'll represent our skydivers. You guessed it, we have gravity pulling down on them. We're not going to have any normal force because they are at a free fall. They are not resting on a surface as they fall through the air, but there is something else that's acting on them as they fall through the air, and that is air resistance. Air resistance, I drew that arrow purposefully smaller or shorter than the arrow for gravity because these guys are moving. So that means that one of the forces that's acting on them is going to be stronger than the force that's counteracting that. So the gravity force is stronger than air resistance, thus they fall downward. That answers number 2, why they are falling. And number 3, why do the skydivers not fall to their death? Well, eventually they're going to open up a large parachute to slow them down. And what that does is it increases the air resistance. So in other words, whenever they shoot their bigger parachute out, that's going to cause the air resistance force arrow to increase in length and counteract gravity a little bit more. So they slow down. The impact isn't as great. All right, one more for you. We've got a car that's driving on a road. Pretty cool car. I wish that was my car. What forces are acting on the car? So this is going to be a little bit different from the last two. Let's draw our square to represent our car. If you look down at your list, you can maybe take a guess as to what forces you think are acting on it. So go ahead and pause the video for a second and see if you can come up with some of them, and then come back when you're ready, and I'll go over the answer. So one of the forces, like the other two, is gravity. Gravity is pulling on all objects that are on Earth, so gravity downward. It's not moving up or down, and it's resting on a surface. So we would have the same size arrow for the normal force because it's on the ground. It is moving to the right in the picture, so we are going to have some difference in the arrows left to right. So to the left, acting against the car, we actually have two forces that are going to be acting against the car here. One is friction, and that's on the tires that are touching the ground. And then the other would be air resistance. To the right, and notice that I have a very long arrow to the right because this car appears to be moving very fast in that direction, would be applied force. The applied force is going to be on the wheels of the car. It's what the engine does to make the wheels turn. So it has an applied force on those, and that's what's causing it to move to the right. So our diagram would look something like that. Okay, last one. This is a classic example. We have the feather and the bowling ball. So you'll see this example a lot in Newton's laws demonstrations. If we drop a feather and a bowling ball from the same height at the same time, which one's going to hit the ground first? Excuse me. So we're going to look at some force diagrams to answer this. What forces are acting on these objects and which will fall faster and why? So we're going to draw two boxes this time, one for the feather, one for the ball. These are both at a free fall, and gravity acts on every object at the same rate during a free fall. So in other words, gravity's pulling on me just as much as it's pulling on the ball and the feather that are falling through the air. So we'll have gravity downward. That arrow is the same for both of these. Same length, same strength of gravity. Acting upward as they fall is air resistance. And you'll notice that the air resistance arrow is shorter for the bowling ball. That's because the bowling ball has much, much less air resistance as it falls. That means that gravity is able to pull that bowling ball down faster than it is on the feather. And that is why the bowling ball would obviously fall faster than the feather. Now, if we took away air resistance, so in other words, if you did this experiment in a vacuum, they would both fall at the same exact rate. So if we could take air resistance out of the equation and just have that pull of gravity, they would both fall exactly the same. And if you don't believe me, watch the video I posted on this on the page on Canvas. It should be right below this one, and that's what they do. They take both in a huge vacuum chamber and take out that air resistance factor, and you'll see how they fall. Pretty cool. Check it out. All right, so here's your guys' homework for today. Here's the scenario. You have a 1 pound soccer ball and a 0.05 pound beach ball. So that means the beach ball is 20 times less mass than the soccer ball. They're both at rest on the ground. You're going to kick them into the air one at a time with the exact same amount of force. If you want to actually, if you have these and you want to go outside and try and do this, you can, but you don't have to. This is all just kind of hypothetical, theoretical work. So there's the scenario. I want you to answer these 5 questions. This will require you to draw some net force diagrams. So make sure that in your Canvas submission you have your diagrams as well as your answers to the question. You can do whatever you want to turn this in. You could make a video, you could do a voiceover of your answers, or you could just submit pictures and sentences if you want. But number one, which ball has more inertia? How do you know? 2, why are both balls at rest before you kick them? Explain using Newton's first law. 3, generate a net force diagram for each ball at rest. 4, generate a net force diagram for each as they fly through the air. 5, which ball do you think will travel farther if both were kicked with the same amount of force? And I want you to really explain your reasoning using your knowledge of forces and Newton's first law there. So use that scientific language, inertia and motion and things like that. So, all right, have fun, guys.